Hello everyone. Let's begin with a curious puzzle. We know Ampere's circuital law, curl of B equals mu naught times J. In symbols, del cross B equals mu naught J. This law works beautifully for steady currents. But here's the twist. Imagine charging a capacitor. Inside the wires, current flows smoothly, but between the capacitor plates there's no conduction current. Yet, experiments show a magnetic field exists there. How odd, right? According to Ampere's law, it should be zero. This inconsistency bothered Maxwell deeply, and it set the stage for a brilliant breakthrough. So what did Maxwell do? He proposed something bold, the idea of displacement current. He said, let's add a new term. The displacement current density J sub D equals epsilon naught times the rate of change of electric field. That is, J sub D equals epsilon naught times dE by dt. This means a changing electric field behaves as if it's a current. It creates a magnetic field too. Think of it like an invisible current flowing in the capacitor gap, perfectly balancing the conduction current in the wires. Suddenly, the puzzle makes sense, continuity is restored. No gaps, no breaks, a smooth, elegant solution. Now here's where things get legendary. Maxwell didn't stop at patching Ampere's law. He gathered all the known laws of electricity and magnetism, Gauss's law, Faraday's law, Ampere's modified law, and wrapped them into four compact, powerful equations. Together, we call them Maxwell's equations. Add to this the Lorentz force law, F equals Q times bracket E plus V cross B bracket, and you've got the complete mathematical framework of electromagnetism. These equations don't just describe charges and currents, they predict waves, forces, and the very heartbeat of modern physics. Here comes the real magic. Maxwell realized that a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. Like best friends feeding off each other, these fields keep regenerating as they travel through space. And voila, you get a self-sustaining electromagnetic wave. Even more astonishing, when Maxwell calculated the speed of these waves, c equals 1 divided by the square root of mu naught times epsilon naught, he found it matched the measured speed of light. That's when the world realized light itself is an electromagnetic wave. How cool is that? Let's test this with an example. Imagine a capacitor of plate area A being charged with current I. We ask, what's the displacement current? Start with the formula. The displacement current density J sub D equals epsilon naught times the rate of change of electric field. That is, J sub D equals epsilon naught times dE by dt. Multiply both sides by A, we find ID is equal to I. Amazing. The displacement current in the gap equals the conduction current in the wires. In other words, current continuity is perfectly maintained. A beautiful consistency that makes the mathematics and the physics align seamlessly. So let's wrap this up. We began with Ampere's law, saw its failure for time-varying fields, and watched Maxwell rescue it with the displacement current. Then, we admired Maxwell's four equations, the crown jewels of electromagnetism, unified under a single elegant framework. From them emerged electromagnetic waves, coupled oscillations of electric and magnetic fields that travel at light speed, c equals 1 divided by square root of mu naught times epsilon naught. The crowning revelation? Light itself is an electromagnetic wave. Isn't it incredible how a simple inconsistency in a capacitor experiment led to one of the greatest unifications in physics? And that's why Maxwell is often called the Newton of electricity and magnetism.